Hey everybody, this is Mr. Bortnick for AP Calculus AB. This is Unit 6, Integration and Accumulation of Change. Today's topic is 6.9, which is integration using u-Substitution. Enjoy today's notes.
All right, welcome to section 6.9, which is integrating using u-Substitution or just substitution in general. The idea of today's lesson is we're trying to figure out how do we take the antiderivative of something that the chain rule has been applied to. So remember the chain rule? That's way back when from chapter 3. We might remember that the chain rule was used to take derivatives of composite functions. And composite functions, you might remember, are functions inside of functions. So the idea here is we're trying to take actually antiderivatives now of things where the chain rule has been applied. We have a similar idea when we take antiderivatives. It's called u-Substitution, which is what we're going to focus on today. U-Substitution. In general, the idea is to look at the integrand, that's the part that's inside of the integral, that's the function inside of the integral, and think about taking the derivative. If the derivative requires a chain rule, then the antiderivative will require u-Substitution. So in general, we're thinking about functions that are composite functions, aka functions inside of other functions, or functions with other functions inside of them. And I think the easiest way for us to talk about this and to do this is to just really jump into some examples. So I want to show you how this works. And the goal here is we're trying to find the indefinite integral, right? We know it's an indefinite integral because there are no limits of integration here. Key idea, remember that when we're taking indefinite integrals, your answers should have a plus c, unless they give you some information that allows you to find a particular solution. So what do we notice? Well, for problem number 1, it's the integral of 3x minus 4 all raised to the 5th power dx. In this case, we see here that this 3x minus 4 is inside of these parentheses, and this is all being raised to the 5th power. This is the inside part. Now, what I'm going to do is I'm going to try to change this problem up so that it's a little bit easier to do. And I'm going to call the inside part, so I'm going to call the inside part u. That's what I'm going to call. So I'm going to say u, and this is going to be side work here. I'm just going to put this over here. U is equal to the 3x minus 4. So u is equal to 3x minus 4. Once you've identified what u is, you want to take the derivative of it. So I'm going to call that du dx. And it's a dx because we're taking the derivative of u with respect to x. That's the variable over here. And so the derivative of 3x minus 4 is just 3. Next, what I'm going to try to do is I'm going to try to get the dx by itself. I want to get the dx by itself. And so I'm going to multiply that to the other side. So du is equal to 3 times dx. Times dx, and then I'm going to divide by 3 to get that by itself, which means that dx is equal to du over 3. Now, why did I do this side work over here? What we're going to do is we're going to substitute, right? This is called u-Substitution, so we're going to substitute in the values that we know. Specifically, I know that we called 3x minus 4 u, and dx, which I guess I'll put here in red, is du over 3. So I'm going to substitute in both of those places here. And so this is going to be equal to the integral of, instead of 3x minus 4, that's going to be u, and it's still being raised to the 5th power, right? We didn't do anything with that. And then that dx is going to become du over 3. So now the idea is, hopefully after you've done your u-Substitution, there's no x's left. Everything is just in terms of u. And then this should be a simpler problem to simplify. So let's try it out. Well, this du over 3 is like, it's almost like a coefficient of 1/3. And since it's just a coefficient, I'm going to bring it outside of my integral and say this is equal to 1/3 times the integral of u to the 5th du. Now this is a way simpler problem, right? This I can just apply the power rule to instead of having all this like complicated stuff that we've got up here. So what do we get when we do it? Well, the 1/3 is still on the outside. If we take the antiderivative of u to the 5th, we're going to get u to the 6th divided by that new exponent, which is 6, plus the c. And so if we multiply out, that's going to be equal to u to the 6th divided by 3 times 6, which is 18, plus c. Now the last sort of step here is, right, we did this all in terms of u, but the original problem was in terms of x. So my last step is I'm going to take this u, that was 3x minus 4, and I'm going to substitute that in for my final answer. So that u that's right here, which I'll go in yellow, is going to go back to being 3x minus 4. So my final answer here is 3x minus 4 to the 6th over 18 plus c. That would be my final answer for problem number 1. Nice. So again, the idea here is if you can figure out what the inside is, you can call that u, you can do some substitution, which will hopefully give you an easier integral to take, and then after you've taken the antiderivative, then you're going to resubstitute back in for u. That's it for this process. Let's try this for number 2. So number 2, the tough part in these problems sometimes is identifying what the inside part is. This one's a little bit more complicated, right? Then this one's got a couple of different things going on. But here I see this x cubed plus 4. It's inside these parentheses. It's being raised to the 5th. That seems like the inside part to me. I'm going to call that u. So u is x cubed plus 4. What's the derivative of that? Well, the derivative of that, we're going to call du dx. That's going to be 3x squared. Next, we want to get the dx by itself, so we're going to multiply that to the other side. Du is equal to 3x squared dx, and I'm going to divide by 3x squared. So that means that dx is equal to du over 3x squared. So again, this is my side work over here. And now that we've got this, we're going to set this equal to, well, the 6x squared stays, right? Nothing's changed. We don't have anything to substitute for that. Our u is equal to x cubed plus 4. We're going to put there where that is. So that's going to be u to the 5th. And then our dx is du over 3x squared. So that's going to become the dx. So that's going to be du over 3x squared. Now, the idea here is after you've done the substitution that if there are any x's, the goal is that they're going to hopefully cancel out. And so what we actually see here is we see a 6x squared being divided by 3x squared. The x squareds are going to cancel, and we're left with 6 over 3, which is just 2. So this is the integral of 2 times u to the 5th du. Again, what happened here? We had this 6x squared cancel with the 3x squared, giving us just the 2. That's right there. We can also pull the 2 out, so that's 2 times the integral of u to the 5th du. And then now we can take the antiderivative. So this is 2 times u to the 6th over 6 plus c. Again, our final step in this is going to be to resubstitute in. Now that we know what the antiderivative is, we need to plug back in for u, which again was x cubed plus 4. So our final answer here is going to be 2 times x cubed plus 4 over 6 plus c. And yeah, maybe I'll cancel that 2 and that 6 out. This looks like it's going to be, oh, don't forget raised to the 6th. So x cubed plus 4 raised to the 6 all over, well, 2 divided by 6 is 3. Plus the c here. So that is going to be our final answer for problem number 2. Nice. What about number 3? Well, got some square roots. We got a numerator and denominator. Yuck. Well, in this case, I'm going to trying to find the inside part. I notice again, this square root of x minus 1 is inside the parentheses. It's being squared. Let's try calling that u. So u is going to be equal to the square root of x minus 1, which, if you remember, is x to the 1/2. And if we take the derivative of that, du dx is equal to the derivative, so 1/2 x to the negative 1/2, and then the derivative of negative 1 is 0. So that's going to be that du dx is equal to 1 over 2 x to the 1/2, or the square root of x. And then if we want to get the multiply the dx the other side, we could say that du times 2 root x is equal to 1 times dx. So that's going to be what dx is equal to. So again, what we're going to do here is we're going to substitute in. We know that the square root of x minus 1 is our u. We know that du times 2 root x is our dx. Everything else we're going to leave the same, and then we're going to see what cancels out. So we've got the integral of u squared divided by the square root of x times du times 2 root x. Well, what do we notice? What do we see that cancels? Well, we notice here that it's a root x being divided by a root x. Those are going to cancel each other out. And this 2 that's here, we can pull on the outside because that's a constant. So this is 2 times the integral of u squared du. And now it's time to take the antiderivative. Now we got a much simpler problem, way easier now. So 2 times the antiderivative of u squared, which is u cubed over 3, plus the c. And then once again, we're going to go back and substitute in for our u to get our final answer. So that is going to be 2, and I'll put the over 3, times the square root of x minus 1 cubed plus c. That is going to be our final answer for problem number 3. So again, what's the process look like? The process is you're trying to find out what the inside is. You're calling that your u. You're taking the derivative and solving for dx. You're then going back to the original integral and substituting both of those in, hopefully canceling any x terms that there are, taking the antiderivative, and then resubstituting back in for u. Nice. Let's try number 4. Number 4, the integral of sine of x times e raised to the cosine x power dx. What's the inside here? Well, the sine is multiplying. It's not really inside of anything. And then this e is again multiplying by sine of x. It's not really in anything. However, this cosine of x here is in the exponent of the e function. It's e raised to the cosine of x. So the cosine of x is inside of the e function. It's the input for that e to the x function. So we're going to call that u. So u is our cosine. And so if we take the derivative of that, the derivative of cosine we know is negative sine of x. So that means that if we multiply out that du is equal to negative sine of x dx, and then that means that dx is equal to du divided by negative sine of x. So let's get that side work out of the way, and let's get substituting. So we can call our u, that's cosine of x, and we've got our du, rather our dx is du over negative sine of x. We're going to substitute that in there. Everything else is going to stay the same. So here's the integral of sine of x times e raised to the, well, not cosine of x, but e to the u. And then instead of dx, we're going to put du over negative sine of x. Now, conveniently for us, what do we see that cancels? Well, we see sine of x and the sine of x are going to cancel out, leaving a negative sign, which I'm going to pull outside of the integral. That's like a negative 1 as the constant. So that's going to be negative 1 times the integral of, well, what's left? E to the u du. And we know that the derivative of e to the x is e to the x, and the integral of e to the x is e to the x. So that's not going to change when we take the antiderivative. It's just going to be negative 1 times e to the u plus c. And then we can resubstitute in our u value, which we know is cosine of x. So our final answer here looks like it's going to be negative e raised to the cosine x power plus c for problem number 4. What about number 5? Well, here in this case, let's try it out. Sometimes the tough part is trying to figure out, what you can do. So here, the inside clearly sort of looks like it's u equals 3x. If we take the derivative, that's going to be equal to 3. which means that dx is equal to du over 3 if we do that. If we substitute in the way that we've got this, we'll substitute in u for 3x, we'll substitute in du dx, or du over 3 for dx. What happens? So this is the integral then of the cotangent of u times du over 3. So cotangent of u times du over 3. And that over 3 is a constant, so we can pull that outside. That's 1/3 times the integral of cotangent u du. And then the question then is, like, where do we go from there? Well, sort of the problem is, I don't really know. I don't know what the antiderivative of cotangent is. That's not really one of the ones that's on our list. And so I'm a little stuck. I gotta think maybe a little bit outside the box for this one. What we can do is we can say, well, what's a different way that I could write cotangent? I know that cotangent is the same thing as, don't forget my 1/3. It's the same thing as cosine of the value being divided by the sine of the value. Okay, well, how does that help me? Well, in this case, we see that there are two parts, but we could technically count this this denominator as its own sort of like inside, right? When we're talking about like an inside function, it's the inside part of a composite function. And what I'm going to do is I'm going to actually do like a double u-substitution here. Now, I don't want to call this new thing u again because we already did that, but let's maybe do w, like double u. It's our second one that we're going to use. So w, which I'm going to have as a new variable, is going to be equal to my denominator here. I'm going to say that that's sine of u. Well, what's the derivative of that? This is my side work over here. So the dw du, why is it du? Well, it's the variable over here is now a u, not an x. So dw du is equal to cosine of u. And if we take get that du by itself, dw is equal to cosine of u times du, which means that du is equal to dw over cosine of u. So, now what? Well, what we're going to do is we're going to substitute in again and just see, how we can get this to work. And so our w is going to be the sine of u. Our du is going to be dw over cosine w. And let's see what happens, or cosine u. Let's see what happens. So this is going to be equal to 1/3 times the integral of cosine of u divided by w times dw over cosine of u. Luckily for us now, what we see is that the cosine u and the cosine u are going to cancel, because one's in the numerator and one's in the denominator. And what we're left with is 1/3 times the integral of 1 over w dw. Now this is like the form 1 over x, which we know the antiderivative is the natural log. So if we do that, that's going to be 1/3 times the natural log of w plus c. And I'm running a little bit out of room here, so I'll go over here. And then what we're going to do is we're going to substitute back in for the w, which has a u in it, which we're going to have to then substitute back in this u over here. So what do we end up getting? We end up getting that this is equal to 1/3 times the natural log of sine of u, but u was 3 over x plus c. Don't forget that plus c. So this was like a double u-substitution problem. This is next level u-substitution problem. I'll just sort of like highlight this in green. This was like what we just did was a double u-substitution. Wow. That's pretty crazy. that you can do that in this one. And really, you know, how did I know that I needed to do that? That's a good question, right? Like, how do you even know you need to do that in this problem? Well, I did use substitution once, and I got stuck. I couldn't go any further, but I knew that I could rewrite cotangent as a different function. Right, as I know what cotangent is, it's cosine over sine, and so I went from there and then was able to solve it. So that is number 5. Wow. Let's talk about 6 and 7, which we're talking now about some tricky examples, as if number 5 wasn't. What? So let's try 6. What's the trick here? Well, in this case, u-substitution is going to be used, but we're going to need to solve for x in order to do it. Let's see it. So what's the inside? Well, the inside here, I see this x plus 1 is inside of this square root. So let's try that out. So u is equal, well, I don't want to change up my color scheme. Let's go back to black. U is equal to x plus 1, and that means the derivative du dx is equal to just 1. So du then is equal to dx. If we substitute in, here's our u, here is our dx, we get the integral of x over the square root of u times du when we substitute in. But that didn't get rid of all the x's. We sort of have a problem now, because actually what this just did is we just made this more complicated than it was. And that's not the goal in this. The goal in u-substitution is to make these problems easier to do. So now I've got 2 variables. What are we even doing for this? Well, one trick that we can do, this tricky example is, well, I want it in terms of u so that it matches these two. So what I'm going to do is I'm going to go to this function here that I've got, and I'm going to actually just solve it for x. So if I do that, I'm going to subtract 1 to the other side. That means that x is equal to u minus 1. And then what I can do now is I can actually take that and substitute in for the x that's right here. And then everything will be in terms of u. So this is the integral of u minus 1 over the square root of u du. And what we can then say is, okay, well, this is the integral of u minus 1 over u to the 1/2 du. And we can see here that this u to the 1/2 is dividing both of these parts. So this is the same thing as the integral of u over u to the 1/2 minus 1 over u to the 1/2 du, or u to the 1/2 minus u to the negative 1/2 du. And then the antiderivative will be u to the 1/2 plus 1, that's 3 over 2, divided by 3 over 2, minus u to the negative 1/2 plus 1 is positive 1/2, divided by that positive 1/2, plus the c. So that's going to be 2/3 u to the 3 over 2, minus 2 u to the 1/2, plus c is going to be our answer for problem number 6. So the trick here in this one was that when we did the u substitution, that not all the x's didn't go away. And so the trick was, well, I can actually substitute in for this x by using this u equals x plus 1 and rewriting it, subtracting the 1 on both sides and seeing that x is u minus 1 as well. So then once everything was in terms of u, I was able to go a little bit further and still solve this problem, even though it was definitely a tricky problem, not a fully straightforward one. Okay. Inverse trig can be confused with u substitution. Well, this is actually a problem here that, I'm looking at it, I'm like, well, maybe 1 minus 4x squared is my inside. But, this is one where if you know your inverse trig functions, your derivatives and antiderivatives, you might recognize that this is the integral, this is the same thing as the 1 over the square root of 1 minus 2x quantity squared dx. In that case, we have 2x is just our inside here. So our the inside part of this function is the 2x. That's the u. So u equals 2x, which means that du dx is equal to 2, which means that dx is equal to du over 2. So we can plug that in, and we know that dx is du over 2, so we'll plug that in there. So this is the integral then of 1 over the square root of 1 minus u squared times du over 2. This over 2 is like a 1/2 coefficient, which I'm going to bring outside. So that's 1/2 times the integral of 1 over the square root of 1 minus u squared du. And if you take a look at this, this is one of our inverse trig derivatives, or the antiderivatives for this. In fact, it is the arc sine. So knowing that and recognizing that, that's going to be equal to 1/2 times the arc sine of u plus c. And then what we're going to do is we're going to plug back in for our u value. Right? We know that u was 2x here. And so our final answer for this one is 1/2 times the arc sine of 2x plus c for problem number 7. Nice. All right, so we've spent this whole lesson so far, number 1 through 7, talking about how we do this with indefinite integrals, right? Indefinite integrals, these ones that don't have limits of integration. We can do this exact same concept with definite integrals. And I just want to show two of these problems for you, and then we're going to wrap up for today's notes. So how is it different with definite integrals? The answer is it's not really, not a ton. There's like sort of just one extra step that we're going to add. So check this out. So looking at this problem, I see it's a definite integral because it's got these limits of integration. Now what I want to mention is notice that this function is with respect to time, or dt, right? And that means that these limits of integration that we currently have here are with respect to t. So t equals 2 and t equals 0 are those. Because the integral and then that dt are working together, they're identifying what variables we're talking about here. Now that's going to be useful for us later because we're going to be changing the variable to u by doing this u-substitution, and we'll see what happens. So what's inside? The inside part, this part under the square root, this looks like that u is going to be equal to t cubed plus 1. T cubed plus 1. If we take the derivative of that, our variable here is time, so du dt is 3t squared. If we multiply dt to the other side, du is equal to 3t squared dt. And then that means that dt is equal to, what's it equal to? It's equal to du over 3t squared. So let's substitute in. We got u equals t cubed plus 1. We've got this dt is equal to du over 3t squared. And so this is going to be equal to the integral, and I'm going to leave it as the integral for right now because we haven't taken it yet, of t squared times the square root of u times du over 3t squared. Now, before I get canceling, what I want to say here is I don't want to keep these limits of integration. My limits of integration here are with respect to time, or t, while the whole rest of this, or hopefully when they simplify, is going to be in terms of u. So how do I fix that? I can't have t here and then u inside. That's not going to work. What I'm going to do is I'm going to use these two values, right? My two limits of integration. I'm going to just plug them into this equation that I've got right here. We know that what u is. So let's substitute in and find out and use that. So I know when t equals 2 that we've got u equals 2 cubed plus 1. Again, I'm getting that from right here, that equation. And so that's going to be, u is going to be equal to what? 8 plus 1, which is 9. So when t equals 2, that's the same thing as u equals 9. Then for the other one, if t equals 0, right, we're using these two values, which came from our limits of integration. We did 2 already. When t equals 0, that's u is going to be 0 cubed plus 1. So u is going to be equal to 1 in that case. So what are our new limits of integration? Well, our new limits of integration are going to be 9 and 1. And that's where these two numbers are about to come from. So 9 and 1, because now these limits of integration are with respect to u. They're the u values, not the t values. And so we want the limits of integration to match up with whatever the variable is that we're taking the integral with respect to. Now, we got some canceling to do. because we also see that our t squared and our t squared are going to cancel. And we're left with this technically 1 over 3, which I'll pull outside. So that's going to be 1/3 times the integral from 1 to 9 of the square root of u du. So now this is a much easier problem for us to do, just sort of looking at this, right? Everything's in terms of u. This is now a way easier problem. All the t's canceled out. And so if we take that antiderivative, the antiderivative of u to the 1/2, or the square root of u, is going to be u to the 3 over 2 divided by 3 over 2. And then since I've got limits of integration here, I'm going to put my brackets to show that I actually do still need to plug in 9 and 1 for this. And because this is a definite integral, we're going to not need we're not going to need a c for this, right? So using our fundamental theorem of calculus, we're going to plug in 9, we're going to subtract, then we're going to plug in 1. And because these are in terms of u, we can just substitute them in right there without needing to even go back to this and substitute in there. So what do we have? We've got 1/3. And then again, using our fundamental theorem of calculus, we have 9 raised to the 3 over 2 power divided by 3 over 2 minus 1 raised to the 3 over 2 power divided by 3 over 2. So that's our FTC. And we've taken the antiderivative and we've plugged in both those values, so I don't have any square brackets anymore. And let's simplify. So we've got, 1/3 on the outside. We've got 2, so 2 over 3, because I'm dividing by by a fraction, so I'm going to multiply by the reciprocal. So 2/3 times the square root of 9 is 3, 3 to the 3rd is 27, minus 2/3 times 1. So that looks like that this is going to be 1/3 times 27 divided by 3 is 9, times 2 is 18, minus 2/3. And so that is going to be, if we distribute the 1/3 times the 18, that's going to be 6 minus 2 over 9. So that's going to be 5 and 7/9. 5 and 7/9 for that, or 52/9 if we want to put it as an improper fraction for that. That would be the exact value of this definite integral, which again, like what did we even just find? Well, we know that the definite integral represents the area between the curve and the x-axis, or the t-axis in this case. So if I were to graph this function, which is a relatively complicated function, if I were to graph it, the area between this function and the x-axis, or the t-axis, between t equals 0 and t equals 2 is going to be exactly 52 over 9. And we were able to find that because we were able to do this u-substitution. Nice. All right, we're on to the last one, number 9. Let's check this problem out, and let's do it. So for number 9, we've got the integral from 0 to pi over 2 of cosine of x times the square root of sine of x. Here, what am I seeing? I'm seeing the inside of this square root is sine of x. So let's call that u. So u is equal to sine of x. If we take the derivative of both sides, we get du dx is equal to cosine of x. So that means that du is equal to cosine of x times dx, and dx is equal to du divided by cosine of x, which we're going to then take that and substitute in for our dx right there. Similarly, we know that our limits of integration are in terms of x, right? These are in terms of x, but we're about to put everything in terms of u. So what I'm going to do is I'm going to write those also in terms of x. We know that our first x value is pi over 2. And if I substitute that in for my u equation, u is sine of pi over 2. And at pi over 2, the sine value is going to be 1 for that. So that's going to be u is 1. And then when x is 0, which is our other limit of integration that we've got right here, u is going to be sine of 0, which is going to be equal to 0 for that. So I've got my new limits of integration, 1 and 0. Those are going to go on my integral. And so we've got those two limits of integration are the new ones. The cosine of x is going to stay the same. The square root sine of x becomes the u, and then dx is du over cosine of x. What do we have now? Well, we can see that our cosine x's are going to cancel each other out. So we have the integral from 0 to 1 of just the square root of u, or u to the 1/2 du. And we can now take the antiderivative. So that's going to be equal to the u to the 3 over 2 divided by 3 over 2 from 1 to 0. And I'll just rewrite that for the sake of clarity. That's 2u to the 3 over 2 divided by 3 from 1 to 0. Because we're dividing by that fraction, we can multiply by the reciprocal. That's where this 2/3 comes from instead of 3 over 2. And we're going to now do our fundamental theorem of calculus. We're going to plug in 1 for our u. We're going to subtract, and then we're going to plug in 0 for our u. So by the FTC, we've got 2 times 1 to the 3 over 2 power divided by 3 minus 2 times 0 to the 3 over 2 divided by 3. And that looks like that's going to be, what, 2/3 minus 0. So our answer here is 2/3. That is problem number 9. So we can do this direct substitution or this u-substitution in problems that are indefinite integrals or definite integrals. Key piece to remember when you're doing definite integrals is that you need to change your limits of integration so that the variables match. We saw that in these two problems. I would definitely suggest this is an important topic, just like chain rule was a really important topic back in chapter 3. Being able to do u-substitution unlocks a lot of integral problems that you'll be able to do. So check out the practice, try those out, check your solutions, and please come to class with any questions that you've got. Good luck on your mastery check, and have a great rest of your day.